Okay, thank you everybody, and great to be here in Hawaii, and great to see so many faces. I guess I got lucky. The weather is a little rainy, so nobody went to the beach yet. So good attendance overall. So again, thank you all for the opportunity to present here. Today, I'm going to talk a little bit about a project we're in the middle of. This is kind of a work in progress related to durability and maintenance of porous asphalt concrete, specifically focused on the Indiana, Illinois region, based on kind of an assessment of this current state of the technology and realizing that we're not using this for good reason. So to start off, I want to thank, of course, my student, Hanan, who is a graduate research assistant working on this project, which is sponsored by the Illinois-Indiana Sea Grant. So just to go ahead and get started, first of all, I'm going to talk about why do we want to use porous asphalt? What's the purpose? For those who are unfamiliar, I know we've got a concrete heavy audience today, so you probably know about porous concrete, very similar ideas for asphalt. I'll review some of the mix design techniques that we use, talk about a case study that we've been doing on some mixes from Chicago DOT, and then get into the conclusions and future studies. So first of all, how do we design a porous mix? So basically, first of all, wait, am I missing a slide? Sorry. That's okay. Okay, we'll go from there. How do we design a porous mix? So first of all, porous asphalt concrete is basically, the idea is that we want to avoid hydroplaning of vehicles, and we want to avoid basically water collecting on the surface of the asphalt concrete. So we want to use porous asphalt because if water collects, vehicles will have a longer stopping time, very similar to why we use porous concrete. Instead, we can use a porous mix that has roughly 20% air voids instead of 4% like a normal asphalt mix, and the water can just drain through that first layer of asphalt and then go off the side to the drainage system as we prefer to do. Of course, there are some disadvantages, which I'll talk about later, but first of all, I want to get into a little bit about how we design these mixes. So how do we design porous asphalt? You know, the typical volumetric design is what we use for dense graded asphalt concrete, right? We do mixed designs based on the volumetrics of compacted specimens to determine the optimum binder content. We have actually quite a few different ways that have been proposed for doing mixed design for porous asphalt. So the first one is that volumetric design approach. Essentially, they use a dry rod test to determine the dry voids in the coarse aggregate. Then we use a compactor for compaction of the specimens. That's very similar to what we're doing now. Other countries still use Marshall compaction. That's another option. Not as realistic compared to the field compaction with a roller that we were just talking about in the last presentation. Typically for porous asphalt, usually we set the minimum void content to 18%, but this is impossible to measure in the lab using the conventional method, right? The conventional method of asphalt is that you saturate the specimen and then measure the saturated weight. Obviously, you can't do that with a porous specimen because if you saturate it, all the water will just flow out when you remove it from water, right? So saturating isn't going to work. Instead, we use a core lock machine where we vacuum seal it or coat it with paraffin wax to measure the saturated weight. And then a lot of times there will be a drain down test. What we mean by drain down is making sure that all the binder doesn't just drain to the bottom of the specimen. Typically for some types of mixes, we use fibers to avoid that. So we can add cellulose or other type of fiber to the mix to avoid drain down. But in recent years, or not so recent years, others have proposed tests we do in the lab. So the Cantabro loss is probably the most common test we do in the lab for porous asphalt, where we just basically put the specimen in this drum with some steel balls, and then we measure how much abrasion is lost with rotations of the drum. There's also permeability tests, many various types that have come and go over the years. We're working with University of Kentucky to run some of those right now. And then, of course, the clogging simulation. This was a really important test because one of the critical issues is that you want to make sure your porous network in the specimen doesn't get clogged with dust. If it gets clogged with dust, that creates a huge issue. Because water obviously can no longer flow through it, so it defeats the purpose of using a porous mix. There are also oil absorption methods where you soak the aggregate in oil, remove the oil and measure the weight change due to the absorption of oil. And then there's a computational method to determine the optimum content. I won't spend too long on that because we didn't focus on that for this project, but the FHWA has a nice method for computing that. Then there's finally visual inspection methods, which are basically based on either the temperature or cooling time. So you either manipulate the temperature or you just let it cool. for a specific amount of time and observe the mix visually. So that's one method. Florida was using that type of method for a while, probably the simplest for mix design. So these are just 3 different binder contents, and you would visually choose the one that looks appropriate. Okay, so getting into the theme of this project, and this is the slide I think I thought was earlier, just again, some background. So here's an image from Nevada DOT that shows a road that uses porous asphalt versus one that does not. Again, we want to avoid the hydroplaning. So we typically want to have a mix that we increase the voids quite a bit. Again, typically for dense graded asphalt or conventional asphalt mixes, we use about 4% voids. Here we want to use roughly 20% or 18 to 20% voids. Again, that void network just allows water to be driven through the road, and this is very important for any area where we might be concerned about flooding, right? If we have a concern about flooding, we want to avoid that, so we use porous asphalt to mitigate surface saturation of water. So for this study, we focus specifically on Chicago DOT, and Chicago DOT has had overall a very bad experience with porous asphalt. So when we kind of came in and said, hey, we'd like to do a forensic study on why some of these things went wrong, they said, sure, absolutely. So we selected 7 different sections. These are the gradation limits, and these are the 7 different gradations that were used for the sections. So you can see that this was, they were all in accordance with ASTM. However, with time, we expect that the gradation will change, right? So we expect that dust will start to clog the specimen, and unless you regularly maintain it, you'll start to have that clogging problem where your porous gradation suddenly starts to shift upward with less percent passing, especially in these finer bands. So that can be a huge problem, and that's something we're looking at with this study. We also chose a variety of locations, some very close to the lake where we maybe expect a little more flooding, some further away from the lake in Chicago, kind of on the south and west side is where they had built these. And here's a list of locations for those who are familiar with Chicago. So our objective in this research, again, was to determine the state of practice that we use for porous asphalt mix design. That's what I presented in the first part. There's also a paper that we've authored related to that, which I'd be happy to share with anybody who's interested. We want to understand, again, how porous asphalt's been used in the Southern Lake Michigan area with a focus on field performance. Now, it hasn't been used too much, again, because there are issues with performance related specifically to freeze thaw is a big one. So we know the porous asphalt is weaker. We know it can't handle too much. It doesn't have a high strength compared to conventional mixes. Again, talked about strengths relationship to air voids. So we know it doesn't have a great strength. You can't use it for interstates or very high traffic roads. But for city roads, the big problem in the north is freeze thaw, right? Which maybe a lot of the southern states or countries that use it don't worry too much about that. But in Illinois, that's a big concern. So for this study, we had 7 sections, 6 field cores from each section. And for this part, I'm just going to focus on the field data analysis and surface conditions. The reason being, again, that I don't want to get too deep into the other stuff that's still in progress, but also the time constraint. So I'll focus specifically on the surface condition. So looking at the surface condition, what we did is we used close range photogrammetry to build a profile of the surface texture. And you can see visually there is a substantial difference between, for example, a section from 2020 and a section from 2014. In some cases, it looks like maybe additional consolidation. So maybe some of that void contents decrease naturally. In some cases, clogging of those pores, right? So those pores have been clogged with dust. In some cases, raveling where aggregates have come loose. Again, we expect that because we know the strength of this mix isn't very high. And finally, in some cases, polishing of the existing aggregate can happen if the aggregate's not of very high quality. So all those things led us to use this close range photogrammetry technique to say, well, we've got sections that were built all the way back in 2008 until 2020. So let's see if there's any relationship. Again, there's a lot of variables between these sections, so you can't make one-to-one comparisons, but let's see if there's any relationship between the age of the section and the surface profile. And what we found here, I won't go through what all of these mean, but essentially this SKU is probably the most interesting one. Lower value of this indicates a very smooth surface. So it indicates very little difference in depth between the surface point and deeper points, which means that essentially these mixes from 2008 have very, very smooth surfaces compared to, say, this one from 2020. And there was a nice correlation for this one. The other parameters here, we didn't observe as much, and I won't get into all the mathematical details of how we calculate those now, but I can assure you that this one makes complete sense that the surface would be smoother as you go further back in time, right? Because the specimens had a lot of time to, again, ravel, again, clog. So all those kind of things are problems. So initially, we do see that porous asphalt deteriorates in quality rather quickly, right? This 0 to 1 is a pretty substantial jump for dense graded asphalt. And you do see that that is just from 2012 to 2020, kind of in terms of when these sections were constructed. So we assume the same is true for porous, and it does represent a loss of that surface texture, which can also affect friction. The whole point of putting this is so that we improve friction by draining water out. But again, it can actually affect the surface friction as well. So what are we now looking forward to? Well, again, few or if any studies have considered the importance of climatic conditions. So one thing we'd like to do in the future, and this is something where we could use partnerships. So please, if anybody is working on this topic or similar topics, we'd love to share in your work and share data. Because we'd like to know in the South, does the surface deteriorate as quickly as it does here? Or in areas where it doesn't, maybe it's not as either not as wet or not as cold. Do you see this rapid surface deterioration, for example, from 2014 to 2020? So we would love to know. There was a previous study in Japan that indicated that 58% of mixes last 11 plus years in warm regions, only 20% in cold regions. And we'd like to see, based on what we see, we can imagine why, again, because the surface has substantially deteriorated from 2008, and in these cases, a higher value is worse. In this case, a lower value is worse. So we can kind of get a sense that since 2008, these surfaces have really deteriorated, and that's 12 years. So 11 plus years in warm regions, but only 20% of mixes make it that long in cold regions. So perfectly makes sense to us just based on the surface, and that's not even getting into the clogging issue. So ultimately, we'd really like to develop a framework for mix design, which accounts for all the freeze thaw issues in the mix that can provide durability in winter. So something that's freeze thaw resistant, whether that's using modifiers, whether that's using a different kind of aggregate skeleton, we're working on figuring that out right now. So summary and conclusions, there are actually over 20 mix design methods with few evaluations of the best overall approach. So there's probably only one paper from Clemson about 10 years ago where they evaluated different mixed design approaches. Other than that, it's kind of a black hole for research. So something to keep in mind for future proposals and things like that. Again, the Chicago DOT study that we did kind of evidences quick deterioration of porous asphalt. And therefore, future studies need to focus on improvement and how we maintain these structures if we want to continue using them in cold regions. It may, in fact, be better that we just decide, hey, this isn't for cold regions, we don't want to use it, but then we have to figure out other ways to solve this resiliency problem. We know that with a changing climate, we're going to experience more flooding events, more extreme weather events. So we need to start thinking about how we're going to handle those if this isn't the solution. So with that, really open to discussion. Again, this is kind of a work in progress. I do want to acknowledge our team again, the Illinois-Indiana Sea Grant, who provided funding for this study, Chicago DOT, who provided us field specimens and some of the field data on performance. Again, kind of noting that, the need for this study. When we started with the Sea Grant, we really didn't know what direction we wanted to go with this project. But after talking to Chicago, it was pretty clear that there are issues and we kind of wanted to work towards solving them. And then, of course, to my student, Hanan, who's worked tirelessly testing materials for this study. So with that, again, really open to discussion, happy to take any points. We're still in the middle of this study, so it's a work in progress. So we, especially when we get into destructive testing, we only have one chance with each of our cores for that. So would love to know your opinions and thoughts on this work. Thanks.
Thank you, Dr. Hajj. Yes.
Mhm. Mhm. Yeah, actually, one of the big challenges is City of Chicago, they didn't have the grades of binder that they use, but we are currently working on extracting and testing them. And one thing we see that's interesting is this is based on my very preliminary assessment of the data, but that the aging gradient is a little bit more severe than what we see for conventional pavements, which we sort of expect because there's more exposure to air through the porous network. So we see the aging gradients a little bit worse, and we see more aging a little bit deeper than we see for dense graded, for example, mixes, which makes sense because when there's cracks, we see the same thing. Related to the aggregate structure, City of Chicago is basically, they're such a huge operation that they kind of indicated that they just don't have the resources to maintain a large porous network. So they kind of let them get clogged. But the most important thing, if you want a good performance, is just avoiding clogging from the beginning. So constantly vacuuming, constantly being in the field, maintaining mixes, because if you don't, basically you're going to have premature issues. There's no question. And porosity will be lost quickly anyway. We actually, again, this is just based on a very preliminary look at the data, but these mixes kind of look more like dense graded mixes with how much clogging has happened. Now there's a large amount of fine aggregate filling those pores. So that's a big problem. Hopefully that answers the question.
Asking what is the average thickness of the porous layer you studied? And the second part is, did you look at the recovered binder, chemistry, rheology?
Yeah, great question online. Again, if you couldn't hear on the mic, it was just if you were online, it was just the questions in the question that's in the chat right now. So related to the binder, that's kind of what I just mentioned, is that we have begun looking at the extracted binder. And again, I think the aging gradient's a little more severe. We don't have all the data for that, so I didn't present it today, but the aging gradient does seem to be a bit more severe because of the higher exposure to oxygen, which we expect. We'll confirm that using a suite of rheological techniques as well as FTIR to look at the chemistry. Related to the other question related to the lift thickness, that was another challenge, is that City of Chicago was not sure about that. So they couldn't provide us much data from the construction. It seems they've had some turnover over the years, and their asset management wasn't great. So we weren't sure about the average lift thickness, but these were a couple of inches. These were not OGFC like ultra thin overlays. Done some studies in the past on ultra thin overlays that are 1/2 inch to 1 inch. These were thicker than that. So these were at least 2 inches of porous asphalt. Yeah. All right. Thank you, everyone.